Hello, here we are once again. It's the Physics 203 video lecture. Physics 203 video lecture 2. I'll begin with some announcements. Let's see what we have here. I had a question about books, and I had recommended Goldstein and Landau and Lifshitz. Those are actually very old classic books. The subject is just so mature, you can find this material all over the place. But Goldstein, just the standard work that everybody has learned from, and Landau and Lifshitz were absolute geniuses. Someone asked about Taylor. I'm assuming that's that big red book. That's also a fine book. I used to have one, and it was sent to me by a publisher. I loaned it to someone, never got it back. But Taylor's also a good book. Maybe you want to have a book or some books, but there is no required book. If you want to buy some books, look around for used books on Amazon, and you can get a whole library for the price of a new textbook, okay? So that's all I'll say for books for now. Zoom sessions will be coming in a week or two, okay? So until then, be patient, and just the best thing I can tell you to do right now in this early formal material, just work on your notes. Space your notes out really wide, and then return to them and fill in with examples and calculations and so forth, and you will, that's the best way to learn. Okay, so where we left off was, well, let's just kind of review what we had there. We're doing what's called point mechanics, mechanics of point systems. And the idea is, can we reduce all of the mechanical phenomena to the behavior of systems of point particles? Okay. So we did that, and we said, okay, we've got a system of n point particles. Mass times acceleration of the ith particle is the external force on the ith particle plus the internal force, which, since it was a set of n particles, they were all the individual forces acting on the ith particle. So j from 1 to n, j not equal to I, Fij. Okay, and then we found that with this formalism, we had the situation where there could be a potential energy. So potential energy function U of R1 to Rn such that F sub I, by which we mean the entire right side of this expression, could be expressed as minus the gradient of U, and the sub I here refers to the ith particle. Good, so that's our formalism. And what can we do with this? We find conservation laws, for starters. I didn't actually give any concrete examples of this. We're working our way through. But you can always think of a system of n gravitating particles. So you could have your solar system, the sun and all the planets. That would be such a system. And we'd take the positions of those to be the respective centers of mass, although that came out at the end of the discussion. Okay? Those positions, since the sun and the planets are not point particles, but we found at the end of the last lecture that we can take the center of mass of each one as being the location, the position. So yeah, what did we have here? We had conservation of energy. So energy T plus U, potential, kinetic plus potential, we have 1/2 some of the individual kinetic energies R1 to Rn is conserved. So we had conservation of energy. We proved that. Then we had linear momentum. This comes under the heading of conservation laws. So we have linear momentum, and that would be total linear momentum equals sum of all individual linear momenta is conserved, comma, if the net external force on the system vanishes. If F net external, referring to the sum of those, which was the sum of all the F sub I external is equal to 0. So then you have conservation of linear momentum. And then what we ended with was, after all, the net external force doesn't have to vanish. Then I'm just going to write here center of mass I'll use capital R for it. Okay, so it's the sum of moments divided by total mass. So we've got this and total mass, center of mass, second derivative equals F net external force. So that's a great theorem because that shows that under the assumptions of point mechanics, an extended body acts like a point mass, which is what we do so often. We talk about the trajectory of a baseball, that kind of thing. And now the trajectory of a planet, we can treat it as a point mass. Its external force would say be the force of the sun on it, and its motion, its mass times acceleration is equal to that net force. But the acceleration of what? The acceleration of the center of mass. So this was the last thing we had on the board last time, center of mass. So I said, okay, we've got a baseball, and then I'll put a little star there. Center of mass is at the center of the baseball. But if we have, a great example is the horseshoe. Okay. The center of mass of the horseshoe is not even located in the solid, in the actual material. Okay. So if you throw the horseshoe, it's going to tumble and do its thing. It's a steel object, so you throw it through air. It's going to have a trajectory of a projectile. But what's going to have that trajectory is the center of mass, and not any other point on the horseshoe. Actually, this point here in space. And so that's why I indicated, if you launch this thing and it does its parabolic trajectory, it's this point. Okay, good. So yeah, you can add some words to your notes, repeat this, always fill in. And now I want to talk about one more conservation law under these assumptions. So actually I'm going to leave those formulas up there. Okay, now I'll send them. I can rewrite these things. Yeah, so this last conservation law, you probably are thinking, well, it's got to be conservation of angular momentum. That's what we're headed for. But the discussion of this one is a little richer than these other two. So the next thing we want to look at is we're taking, same thing we did with linear momentum, by the way. So now let's look at, so let's go ahead and write this out. So we have m sub I. Okay, so we're starting out the same way. But, oops, not that way. The external force is plus, I'll just write J, Fij, the internal forces. This time we're going to take the cross product of this thing from the left. So we're going to go like this. R sub I cross, and leave yourself some room here. R sub I cross M sub I, R sub I second derivative equals, and okay, I'll do the summation right away. We're going to do the summation, so we got to have room for the summation here as well. Okay, but since we have an equality here, we do a cross product on the whole thing and then sum over it. We certainly still have an equality. So now we have R sub I cross F sub I external. It's over I plus sum over I, sum over J. I is not equal to J. R sub I cross F sub I J. Okay, so if this is an equation, then this is also an equation. And now we have to inspect this thing. Our goal is to show that this double sum vanishes, but it doesn't vanish quite as easy as the other one vanished. Okay, so let's first note that as before, we have a lot of pairs. So we have R sub I cross Fij plus R sub J cross Fji, right? We have a whole bunch of pairs like this, and we can't just say that they vanish yet. But the next thing we do is say, okay, then that's R sub I, I'm going to write this down and I'll explain it. R sub I minus I sub J cross Fij. Now, why is that? The reason is that Newton's third law says that Fji is simply equal to Fij with a minus sign in front of it. Okay, so that's how I can get this step here. Now, the third step, these can be assumed, or this cross product can be assumed to vanish if Fij is the central force, equals 0, comma, if Fij is a central force. And I'll remind you what that is, and then you'll see what's going on here. A central force, and I'll use this space right here, by the way. A central force, okay. We will even have a section on central force this semester. We're going to study it formally. Right now we're just using its definition. So what is a central force? That is if you have your 2-point particles here, ith and jth point particle. Okay. This is R sub I, this is R sub J. You bring in another color into the mix. So this red vector here what is that? That difference vector is R sub I minus R sub J. Okay. And a central force is a force between two particles that is directed along the line joining those particles. So if we have a central force, then R sub I minus R sub J and Fij are parallel. And if those are parallel, then their cross product vanishes, okay? So here I'll write equals 0, and right here I'll write because they're parallel, because Ri minus Rj is parallel to Fij. Okay, so the upshot of that is that this vanishes, and now we have to discuss this right here. Okay, so the double sum vanishes, and remember, this is the collection of all the internal forces. This time, for them to vanish, we have to have central forces as well as Newton's third law. Okay. So now we're going to look at this thing here, and what we'll do is take the time derivative of the sum of R sub I cross M sub I R sub I dot. One derivative, a one-time derivative. And what we see is, this is sum of R sub I dot cross M I R I dot plus sum of R sub I cross. So the time derivative of this left side is equal to this because these two vectors are again parallel. R sub I dot R sub I dot. They're parallel, therefore this sum vanishes, 0. So we can put everything together now. And we'll get our third conservation law. You know, I think I'll put it here under this remaining space, just to fit it all in on one board. Bring this down here again. Okay, so what we have here is now d dt of this sum is equal to what was left right here, which was the net external torque. Sum over external. And this is the angular momentum. This is its time derivative. So the time derivative of the total angular momentum of the system is equal to the net external torque on the system. Let's see here. Yeah, we'll go ahead and erase this. So continuing what we have down here, for d dt of L for the vector angular momentum is equal to the net external torque on the system. I'll use a lowercase l for lowercase l for the individual angular momentums. There's the total out of that expression there. And again, same for the torque. Tau sub I is equal to sub I cross yeah, so we have this law right here, and if the net external torque vanishes, then we have the conservation of angular momentum, right? Then L total is constant. So now we have our conservation laws: linear momentum, angular momentum, energy. 3, 6, 7 conserved quantities altogether. Three components of a vector for each angular and linear momentum, that makes 6, and then energy is a scalar, that makes a 7th conserved quantity. Okay, good. So that's the big framework. That's the framework of classical point mechanics. This is not the form in which we solve a lot of problems, by the way. For that, we're going to develop Lagrangian mechanics, where we can deal with systems with many degrees of freedom more systematically. But so far, so good. I think I'll end with a board for examples for this. I'll talk about the central force problem, and how about we just set it up right now briefly. The central force two-body problem, or the central force n-body problem. We'll just set them up. We're not going to try to solve them. Later on in the semester, we'll do the two-body problem. Maybe talk a little bit about the three-body problem as well, although we have plenty of other things. But let's see here. So now we have the point mechanics example. Two gravitating bodies. Gravitating bodies. We have Newton's law of gravity. We have 2-point masses, although they're actually finite spheres, the sun and the earth, for instance, sun and any other planet. So an n-body system would be our solar system. And if you add, depending on how many of the comets and stuff and asteroids you add to it, the number n could be very large. Okay, so two gravitating bodies. Let's go ahead and write this down. We've got M1 and M2, and this is in fact just what I had just done a minute ago. Okay, you have R1 and R2, and the first thing, we could just write down Newton's law. There are two gravitating bodies, and they are not in some external field. It's just those two bodies. So then we have M1 R1 acceleration equals F12, and we have M2 R2 equals F21. Okay. Now what are these forces here? F1 and F2. Well, F21 is negative of F12. Okay, that's by Newton's third law. So first of all, we can say by Newton's third law, F21 equals minus F12. And then the law of gravity, we have good. 2 on 1, I'll just leave that right now. So the force of 2 on 1, very good. This is R1 minus R2. So that force there, F, is equal to minus G, M1, M2, divided by the square of the separation distance, R1 minus R2. Difference of those vectors, take the magnitude, square it, And then there's a direction vector. So R1 minus R2 points to M1, so the minus sign means I'm going to be pointing away from it. So here I would have R1 minus R2 vector divided by R1 minus R2 magnitude. So now you would take this, plug it in here, same thing with a minus sign and plug it in here, and then you have Newton's laws. Not in the form that you can easily solve them, okay? But that will be our point of departure. It's a really interesting development. If you haven't seen the central force problem for a while, very interesting development to make it all the way through to what we call the Kepler problem. But as far as the formalism we had just been describing, we've got that right there. So linear momentum of this set of two particles in space is conserved. Angular momentum is conserved, the sum of the two angular momenta. Now the next thing you do, going through this program here, is take the center of mass as your natural origin, okay? So two gravitating bodies, next. Take the center of mass as the origin, okay? And I always like to draw a little star for the center of mass. Suppose this is the larger of the two bodies, center of mass is closer to it. So that would be your new origin, and then you would express these two vectors now, since they just described these positions, with respect to that center of mass. Because that center of mass is moving uniformly through space. Okay, so we just take it as the origin and get rid of that motion. Yeah, so that's how the program is started. You can also do this for n gravitating bodies, which will be a lot more complicated. We've got the center of mass. Okay, there's one more ingredient we'll take a little more room for. And that ingredient is that we have these forces, this force right here, and we want to, of course, express it in terms of a potential energy. So if we write that down, we'll be complete. Or it'll be a good place to end this little section here. So what about the potential energy function? So next, find U of R1 comma R2 such that F equals minus gradient U. Okay. And in fact, the force on the one particle 1 is the gradient with respect to the 1, and force on particle 2 is the gradient with respect to the 2. And what that is U R1 comma R2 equals minus G M1 M2 just over the magnitude R1 minus R2. And you know what? I'll put this as homework. Who wants me to put this as homework? Why not? Homework. By the way, I didn't have to have the second subscript there. I could have just said F1 and F2, right? Show that F1 equals minus gradient 1 of U, F2 equals minus gradients of 2 of U, and that's just minus F1. And what you have to do is take the gradient of this 1 over r function here minus the gradient. And that should come out. And the second one will be trivial, because when you take the derivative with respect to r sub 2, that minus sign will give you that extra minus sign that reverses the thing. So yeah, then you're actually complete. You've set the thing up as far as we can at this stage of the game, okay, in terms of our formalism. Okay, good. So that'll be the end of this section. We've got so much to do. We're headed for the variational calculus and Lagrangian mechanics. So this was just Newtonian point mechanics. Okay, and like I said before, we'll come back to this whole problem when we solve the central force problem and the Kepler problem. And we can extend it a little bit and discuss the three-body problem as well. Okay. Good. Okay. Here, actually, I'll give a little hint on this thing. So suppose we have f of r is equal to 1 over r, okay? And r is equal to the square root of x1 squared plus x2 squared plus x3 squared. Okay. So what is the gradient of f of r? That is minus 1 over r squared times the gradient of r equals minus 1 over r squared times r vector divided by r scalar, r magnitude, because dx of I of x1 squared plus x2 squared plus x3 squared is equal to 1/2 root x1 squared, x2 squared, x3 squared times 2xi, the 2's cancel, is equal to x of I over r. Okay. So that's the fundamental relation and calculation you have to be cognizant of to do this work right up here. Okay. And in these examples, instead of this lowercase r, so above, we have this expression here. We have x1 minus x2 squared plus y1. Yeah, I'm kind of mixing metaphors here. y1 minus y2 squared plus z1 minus z2 squared. Okay. And if we take the derivative with respect to the 1 or with respect to the 2, we get the opposite sign, but the same thing. So yeah, work on this as well, and then you can pull that off. Okay, let's see how we're doing time-wise here. Wow, okay, very good. Okay. Well, now we're going to start a new section, but it actually picks up with the point systems again under a slightly different aspect. So I'll give a title to this. This has a long title. Point systems, forces of constraint, virtual displacements, and D'Alembert's principle. Okay, so that's a mouthful. Point systems. That's what we were just talking about. Forces of constraint. Virtual displacements. And D'Alembert's principle. Okay. That's a board-filling title here. So, yeah, D'Alembert. Okay, let's write down our point system again. Slightly different. So once again, we have n particles and Newton's law, but this time we're going to just write an external force as before that they're subject to, and a force of constraint, and I won't give it an extra title, I'm just going to say F sub I like that. So that's the force of constraint. And you could say it's just the sum of the internal forces. But it isn't necessarily the forces of the other n particles. Okay, it could be some constraints that that act on the particle in a different way than just being the forces of the other particles. And the simplest example, and we're going to use this, is the pendulum. So you have a point M on a pendulum, simple pendulum of length L. Okay, and so this is from the out, or at the beginning is a pendulum. Okay, plane pendulum. Therefore, it's a point in 2 space, has 2 degrees of freedom, but this string is a force of constraint. Now the nature of the force of constraint is that you don't know what it is necessarily. Actually, if you want to find that out, you have to maybe calculate it. But the string constrains this particle to move along the arc. Okay. So that's what we're talking about in a more general sense over here. Forces of constraint that constrain the particle to move in a certain way. Okay. So that's the first thing. So we have point systems, we have the force of constraint, it's represented over here. And now we want to talk about what a virtual displacement is. A virtual displacement, we're going to call it delta R. A virtual displacement is a displacement that's consistent with the forces of constraint, consistent with the constraints, consistent with what the system can actually do. Okay. But it's not actually part of the dynamics in the sense that, I'm going to write here delta R sub I, delta R, virtual displacement. If the pendulum is at this point, then the virtual displacements that are possible are this one and this one in the other direction. Okay? But we're not saying they're actually happening, we're saying they're possible. And what we'll have in general is that we're thinking of frictionless systems, okay? Because our principle that we're going to invoke in a moment, D'Alembert's principle, is based on the idea that the virtual work. So if you take the force times the virtual displacement, it does no work. And that will be the case with this system here. That's why the pendulum's a really good one to look at, because what is, I'll do it in blue, what is this force of constraint other than the tension in the string, right? And we don't know the tension of the string from the outset. It's not just mg or something, okay? So the force of constraint is the tension of the string. Just by definition of a circular arc, we can see that these two vectors are perpendicular. And since there's no friction in there, there isn't going to be any component of force in that direction at all, okay? And so the work done by this vector and this tension, which is the force of constraint, is going to be equal to 0. Okay, so I'm going to write those things down now. So we have virtual work, constraining force times the virtual displacement equals 0. Principle of virtual work. So now what I can do is take this equation here and just rearrange it. Okay. I'm going to write sum of f sub I, these here, equals minus sign is just here for formal reasons, but that means I'm got this here, so f sub I, oh, not so fast. We wanted to do this, what I just had right up here, delta r sub I is equal to, here we go, sum over f sub I external m sub I r sub I second derivative dot delta r sub I. Okay, so we took an equation which was just this equation. And the principle here states that this is equal to 0. The sum of all the virtual work equals 0. Therefore, we have the external forces minus this here, dot dri, equals 0. And what you'll see is this is another way of eliminating the internal forces from the formalism the way we did, well, analogously to what we just did with our point mechanics. Okay, we've eliminated the internal forces, so this now is 0, and this is called D'Alembert's principle. Go ahead and write that down. D'Alembert's principle. Now these virtual displacements are just very similar to regular geometrical displacements, except they're not actually part of the time dynamics of the system. In a sense, it's what could be. You know, if you had a system and you displaced it in ways that are consistent with the constraints and took this scalar product, okay? This here would represent the true motion of the system, because this is only true or when Newton's law holds true. There's another way to put that before I go on, and then we're going to do some manipulations on this thing. This vanishes when Newton's law holds true. If you're in the vicinity of the true trajectory of the system, and you do a dot product with a possible displacement of the system, okay, then that dot product, and under the assumption of frictionless motion, basically, that dot product will be zero. Okay, so if you're outside of actual Newton's law, then this dot product is zero. If you're actually right on the true trajectory, then it's zero from the get-go. Okay, so what we want to do is manipulate this expression and turn it into an equivalent principle. How are we doing time-wise here? Well, moving right along. Let's see. Okay, let's do this. This is a pretty formal calculation. We want to make it to Hamilton's principle of least action. So there are a couple of ingredients here. And the formalism with the virtual displacements goes like this. So virtual displacement formalism. So, but first of all, because it's outside of time, so to speak, the virtual displacement with respect to time is equal to zero. Okay. And what that means is, if you're looking at a time derivative of a virtual displacement of r, then you can exchange these two operations. So that is equal to the virtual displacement of the velocity vector. Okay. So we can formally exchange these two operations here. Okay. So those are actually the two main rules. Next thing, I'll write down the following. I'm going to be multiplying out this r sub I second derivative vector with delta r sub I and reformulating that. So I'll go ahead and do this calculation as well. I'll just put it down for us and then discuss it. And then we can put all the pieces together. So we have r dotted into dr like this. That is d dt dr. And since we're looking at the product rule here, chain rule, d dt delta r. And this is the one that can make use of this rule right here. Equals dt. Okay, and this one here, let's go ahead and write this like this. Minus variation 1/2 r dot squared. Okay. So let's look at this here. If you were to take this derivative here, you'd have second derivative there, and then plus this one, which would give us that one right there. Okay, so that's why I just brought this one over from the other side, because I was just isolating this one right here. Okay, now I invoke, I recopy this one down, and then this one here is off of this property, and this is, so to speak, the integration of antiderivative of this one here. If you do this here, you 2 cancel the 2, and you get that one right there. Okay, so yeah, this is the ingredient we need to reevaluate this expression in the box. And I'll leave this here and I'll have enough room and we'll discuss the thing. Okay. In fact, I'm going to can't skip as many steps as I would like to. So skip that many steps, so let's put this one in here as well. So we're going to bring in the idea of the potential energy right now. So we have this sum, right, with this product, and the second one with the masses. We actually already dealt with this one in that calculation there, so we just have to plug everything in. So sum over F external dot delta R sub I, that's this one right here, is equal to sum over M sub A. So first I'm just rewriting this thing, one on either side. Okay. So I'm just rewriting this thing. But now, this one we can see is minus variation of the potential energy. Okay. Whereas on the right side, we have the result that I put up there, M sub I T sub I dot. I'm just putting the subscripts on. Sum over M sub I 1/2 squared. And this here be the variation of the kinetic energy. So yeah, make sure you have enough room in these. You can see how I plugged these in, and now I'm identifying this as minus this essentially, because it's just spatial derivatives, it's like a gradient of u, okay? So that gives us this force dot dri, external force. So that would be the gradient for the external forces. This is the substitution according to that chain rule there, product rule. And this we recognize as m over 2 v squared. Since these are both scalars, we can pull this outside and we have a variation or delta kinetic energy. And now we can put this together and we're almost at Hamilton's principle. Now we'll bring this to the left side. We have kinetic minus potential energy equals m sub I d dt r sub I dot r sub I. Okay, I'm going to put a box around this because there's a fair amount of stuff hidden away in here. But we have a complete time derivative. And so one thing we can do with this expression here is integrate it with respect to time. Okay, so we'll integrate this thing with respect to time between fixed boundaries. So this identity here, the integral t1 to t2 t minus u dt. This side, if we integrate a complete time derivative, we just get the function here. So this is equal to m sub I r sub I dot r sub I from t1 to t2. And now we make a further stipulation. Namely, we're going to require that these virtual displacements of the system at times t1 and t2 vanish. That is to say, we've got the system point 1. This represents its trajectory between points t1 and t2, the old mechanical system. We're going to request that any of these virtual displacements at that point at these points 1 and 2 in the trajectory of the system vanish. Okay. So t1 r sub 2 r sub I of t2 equals 0. So this is where this famous picture comes in that you always see of your variation of the trajectory vanishing at the endpoints. Okay? Under those circumstances, this vanishes, if this holds true right here. Finally, because the delta operation takes place instantaneously, we can take it outside of the integral and we have our principle. Integral t1, t2, t minus u dt equals 0. And this integral is referred to as the action, and this is the principle of least action or stationary action. But truth be told, all of these stipulations seem kind of vague at this stage of the game, but as we develop the variational calculus, we're going to nail them down very accurately so that there's no ambiguity to them at all. Okay. Yeah, there's actually a lot of subtleties in this whole development that you could look up in a book and spend a lot of time going through. But this is what we arrive at, called the principle of least, it's a maximum, minimum problem. So you say least action. Formally, it's actually stationary. So maximum, minimum saddle is one way to look at it. Okay. So that's where this principle comes from. In the upper division class, I never do this discussion here, and what we do is we start with this and then prove that it gives us Newton's laws, and we're satisfied with that. But now we're using this and we want to motivate the meaning of the variational calculus, and this is one train of thought for the meaning of the variational calculus. So we have L equals difference between the kinetic and the potential energies. We call that the Lagrangian. And this integral L dt we call the action. Very important that the whole derivation required us to have fixed endpoints. We'll actually investigate this thing in many different forms, or a number of different forms during the semester. So with the fixed endpoints is the principle of least action here. And When you don't have fixed endpoints, it actually becomes a function of the coordinates and the time. So yeah, the action we're going to see a lot throughout the entire semester. Okay, but this is how you get the principle of least action, also called Hamilton's principle. And the point here was you can take Newtonian point mechanics and then introduce the concept of virtual displacements and some couple of stipulations, and that's where this principle actually comes from. Like I said, what the next step is to put a very specific and rigorous meaning to all of these operations here, which were a bit hand-wavy at the moment. Okay, so let's see how we're doing for time once again. That's already 1 hour. Well, 1 hour, we don't really want to do much more than an hour at a time. However, I'll go for a few more minutes. But yeah, one thing you can do on this section is make sure you go over these various steps here and fill in some words for my hand wavy things. If you actually make sure you do these steps, plug them in, you can see what I assumed and what I didn't assume. For example, you might want to investigate this identity here, okay? And this identity here makes sense of it. So this delta can be used like just a total differential. So formally and mathematically, you could treat it like the total differential, except it has these additional rules in terms of the time. That's formally a way to look at it. Total differential, but rules where you can exchange with respect to time differentiation. Okay, good. And we have, okay, so we have what's on the upper board. And I'll just, for the next few minutes, just kind of give a heads up for where we're going with this. With all of the rules that go with it. So next I'm going to write variational calculus. We're going to develop the formal rules of the variational calculus, and we'll see they parallel what we required in order to obtain this expression. And once we have the variational calculus, then we'll apply it to the physics scenario, because it's actually an interesting mathematical theory in its own right. So first we'll just study it mathematically, and then we'll go back to the physics content. But so for variational calculus, what do we mean when we say variation, some integral f of, use some different variables, y prime and x dx equals 0. Okay. So this is the formal version. What we had here was L, since it was from the potential energy and the kinetic energy, L was a function of R1 to Rn, R1 dot to Rn dot. We'll leave out T for the moment, dt. Okay. This is what we, let's go ahead and erase this. This is apparently what we have right here. So we have function of a coordinate and its derivative. Okay. We're going to study function of what we're going to call a coordinate and its derivative. Okay, function of a variable and its derivative, and here's the parameter. Okay. Good. And that's gonna, that needs a whole fresh lecture, okay? So we'll go ahead and study this next time. And probably, you know, in a long lecture, we can do this to the degree we want to study it. And at the very end, we'll actually be able to come back to the Lagrange, and then we'll be back in Lagrange mechanics. Although it's possible we'll take this another lecture just because it's such a great subject. Okay, so I'm going to leave it right here. And good. See you next time.